Okay, good morning, everyone. Thank you for joining us today. I'm going to give it just about a minute for the rest of our audience to continue joining the webinar. I would love to turn this over to Blake Teipel, who is today's presenter and our new Chief Strategy Officer here at Nexa 3D. Hi, Blake.
Hey, Lewis, how are you, man? Good to see you.
Doing good, doing good. Thank you for joining us today to talk about HSE.
Oh,
Um,
yeah.
You are going to be a soon-to-be very familiar face with Nexa 3D. So would you take just a brief minute to introduce yourself, kind of your history, and a
Oh,
little bit of how you got to where we are today with high-speed extrusion?
yeah, absolutely. Thanks, Lewis. First of all, I'm delighted to be here. Talking about, high-speed extrusion is one of my favorite things. So a bit about me. Try to keep this brief. So I'm a manufacturing and design engineer by training. I worked for about 5 years for Caterpillar in a factory where we were designing, precision hydraulic parts and hydraulic components in Central Texas, and we actually built a factory to launch a brand new product line. I was very fortunate to be part of that team that brought a new facility online. Prior to that, I worked for a time at John Deere Power Systems in Iowa, in the United States, and I had design responsibilities for a few of the subsystems on some of the 6.8 liter and 4.5 liter diesel engines. Always have just loved the idea of building stuff and creating new parts and components that have to go into production. And so later on, I went to school for materials science and ended up completing a doctorate in materials science at Texas A&M. Gig 'em Aggies for any Aggies on the line here. And if you're not an Aggie, that's okay. I still love you. But we also then launched Essentium originally as a materials company, so kind of materials first, sort of how we came to the marketplace. And then, later on along the way, we said, man, we really need to design and put a system into the world that, is an industrially relevant, high-speed system that can give control points to users. Because as I was thinking about my time at Caterpillar, and as we were putting the factory together and we were deciding what machine tools do we put on the floor, we engaged in sort of this actual manufacturing flow where you said, well, I need a machine tool that talks to, a software system that talks to a machine downstream that reports, and gives control points back to the engineers and the machinists and the technicians at Caterpillar. And so we designed at Essentium the high-speed extrusion system to be like a machine tool. And I'll get into kind of what that means and how we interpret that and how we mean that to go here in these pages. But just know that our goal was always to provide a machine that is an open architecture system with control points that you guys and your, again, your user base and so on actually has the control, not us. That was always our goal. And I think that's what we've been able to deliver into the marketplace. So Lewis, if you're wanting me to keep going, I'll go ahead and keep going into the content here.
Yeah, let's go. Take it away.
All right, man. So we're going to dive in today. Again, so now Essentium is part of the Nexa 3D family. So we are a Nexa 3D company. We have joined into the Nexa 3D universe. We are super thrilled about that. Now the ability to access all of Essentium's classic technologies is possible, I think, at even greater scale, right? So you can basically access now through the Nexa 3D customer ecosystem and go-to-market ecosystem. And so we are bringing the products now, to even more users and a broader user base through the Nexa 3D architecture. And I'm really thrilled about that. So let's talk about kind of what that means. So when we talk about high-speed extrusion, again, I just want to give you kind of a high level and a bit of an overview of how we thought about this product. It's an open architecture, high-spec system. So when I say open architecture, what I mean is it's a G-code based system. So you can run, the slicers that we support, or if you have your own slicer, you can run your own slicer. The machine runs off of G-code, and it runs off of, the same kind of G-code that you can run on an Ultimaker. We have custom scripts in terms of headers and footers and things like that prepare and orient and home the machines. But if you're familiar with the G-code architecture, that's the type of code that our machine runs on. And we give users access to the G-code. So, that's wonderful and it's terrible at the same time, because you have the freedom to crash the machine. You have the freedom to jam your nozzle. You have the freedom to have a great print, and you have the freedom to have a terrible print. Just like if you were operating a CNC mill, you could crash the tool. You could, you know, you have the freedom to design and control and be that master of your printed part destiny with our system. Of course, we have guide rails. Of course, we have slicing profiles. We have, you know, a lot of effort has gone into making, you know, that user success and first time print success and all those things come in at high rates. And we've got great training, great customer support, and all that's going to continue through the Nexus system. But just know that you as a user, you can change all the parameters you really want to in the print, and you know, and that gives you an ability to dial in your part and dial in your geometry, and that's something that we combine. So a couple other points that are on the page here. Again, high degree of user control, as I mentioned. Essentium really was a materials first company, and to this day, you know, materials remain near and dear to our hearts. We've got a materials production factory in Austin, Texas, where we produce all the grades of filament that are available across the Essentium ecosystem, and those specific grades that have been pre-programmed with the slicing profiles and available on HSE, and I'll talk about that. HSE's got over 100 systems field deployed, many of which are deployed in military applications and bases and so on, and then many of which are deployed, you know, at an industrial customer setting, and I'll talk about that. But now, again, in combination with the Nexus 3D go-to-market and commercial team, we are excited to really take this up to the next level and really support and help this capability become available and accessible to a much broader audience. So we've been able to deploy systems across really every blue chip and industrial customer base, starting with government and military users on the left-hand side, up to, you know, kind of aerospace and defense, industrial, biomedical, and so forth, as you can see. Certainly the areas where we focus on the most, I would certainly say, are kind of the left three kind of, you know, banners there. So certainly government and military, which of course, you know, have a lot of crossover into the aerospace and defense world. But then the industrial world. Industrial is a broad, you know, sector. It touches a lot of the manufacturing and sustainment and parts and supply chain aspects of basically, you know, the industrial community. And so we've got many customers in that section. And of course, you know, not to leave behind biomedical, automotive, or contract manufacturing. As we'll get into in some of the later content, some of the materials that Essentium offers have been custom engineered really for the contract manufacturing, you know, vertical. And so what I mean by that is we have materials that are ESD, or electrostatic dissipative safe, but they're also clean room safe. And that's a really important distinction. We have materials both at low temperature ranges and at high temperature ranges that can go through things like wave solder ovens and reflow ovens, and, you know, be useful in contract manufacturing workflows where you've got sort of printed circuit board and printed circuit board assembly and electronic device assembly and so on. So I think that's a key area to focus on. If you're a user, you now have a system that, you know, really has been thought very deeply on to work with sort of semiconductor industry, and again, electronic manufacturing of devices and boards and so on. But it started with the materials. Again, do these materials survive? Do these materials make sure that they don't leave behind a conductive dust or a conductive residue, which a lot of the other materials out there do, and we've benchmarked those, and so have our customers, and in some cases we are the only qualified material for use inside of certain factories. So I think that's, you know, certainly something that bears mention. Again, just diving more into a little bit more of the detail on the high-speed extrusion platform. I won't get into really all the specs. I would certainly direct your attention to our website. Our website has gone into great detail on both the HSC 180 and the HSC 280i machines. And so, you know, a lot of details found there. But at a high level, we've got, you know, an XY stage at the top of the printer. Then we have, you know, a Z tray that descends and is controlled by three independent ball screws, you know, sort of two ball screws at the front corners, one ball screw in the back. And then we've got, you know, filament feed up the sides. We have filament canisters across the bottom. The machines are supplied at the time of sale with two canisters. If you want to store additional materials on the machine or at the machine, you can purchase additional canisters. The machine will hold up to 6. The user interface is off to the side, and so you can walk through either a touch panel user journey, or if you're more comfortable with a keyboard and mouse at the moment, the keyboard mouse is still available. Over time, we're going to migrate more towards, purely a touch panel based interface. But at the moment, certainly you can, use our user interface either way you want, which again is very similar to what you can see with mills and lathes and so on. In many cases, you've got sort of pointer-based control and so on. And so we decided to go that direction to make the machine, accessible to those technicians and users that are familiar with the CNC type journey. It's important to note the drag-free filament system here. I just want to say a couple of words about that. So the way that the machines are actually laying down the material, it's all servo motor, closed loop. In the motion stage uses linear motors, by the way. There's no belts, there's no pulleys. These are, again, high-spec linear motors. So you get the same positional accuracy close into the XY home as you do at the very end of the axis, whereas with belts and pulleys, you get stretch and you get certain things that actually the further away from home you get, the lower your part accuracy is because, of the lash and that's inherent in those types of motion systems, which is why we went with a linear motor-based motion system. But the motors themselves, all of the motors on the machine are closed loop servo axis motors. So you actually get feedback in the machine when you go out to the position of where you want to print the part. The motor will tell you, hey, if you wanted to go 200 millimeters, you went 200.001, and it'll tell you where the geometry is. So you get a build file after each print that'll show you what the geometry is of the printed part that was just produced. So if you want on-machine QC, on-machine QA, especially if you're working later in a downstream step with 3D scanning or metrology or something like that, then you can verify and validate the part geometry that was produced on the machine, and you can correlate that to your process quality control and to a high level. And by the way, our motors sample at 16 kilohertz, so you get a very high accuracy, high resolution sampling rate. That's important because you get a great picture of what the printed part is that you get off the machine. I'm not aware of any other extrusion systems that can match that. Okay, the reason why I'm emphasizing this point is because if you or your customers or your user base are really interested in making sure that you understand the geometry of the printed part that was produced on your machine, and if you're going into a production application where you've got to make 200 or 2,000, and we've had customers do both, we've had customers do 10,000, they need to be able to say, okay, was part one printed, and does that geometry match it, part 55 and part 6,423, and they have the data now to validate and back that up. So that's what you can get with our systems. Our systems are able to go at incredible rates of speed. Our systems can also go slow. It depends what the user wants to do. If you want to, let's say you've got an overnight print and the time to part is not the most important feature, you can slow the machine down, run it again like a classic FDM system at the same speeds of classic FDM. If you've got a classic FDM build file, then you can run that on our machines and it'll go the same kind of speeds. But if you're dialing in a part and if you're dialing in a production application, then you can run the system at hundreds of millimeters per second while printing. And that'll give you the ability to produce batches of parts way faster than any other extrusion system that's out there. And that's the point I want to emphasize. If you have batches, if you have repeated part production, then turning to an HSE will be awesome because you have the same performance as classic FDM for a single part. But when you need to print more parts, you can dial in geometries, you can dial in G-code, you can optimize the process, and you can really fly. And that's how we built the system. So we've got two different models. Okay, we've got an HSE 180, and we've got an HSE 280i. So I'm going to talk about the 180 here first. The 180 is actually split into three different kind of submodels, and these are pertaining. The submodels are pertaining to the temperature ranges of the system. I see that there's a question, by the way, and so I acknowledge that. We're going to get to the questions here just at the end. So you're not going to lose your question. We will absolutely get to it. And if we go back in the content, I'll go back in the content to wherever your question is. So just know that we want to collect your questions, by the way. If there's any other questions, please go ahead and submit those and we will make sure we get to those. But as far as the 180s go and the line, we've got the low temperature version, the standard version, and the high temperature version, okay? And so the low temperature is basically an enclosed chamber, but it's not insulated and it's not actively heated, okay? So if you want a utility machine that is there for fixtures and jigs only, and I don't care about aerospace materials, I don't care about automotive materials, then a low temperature, an LT could be a perfect machine for you. It still uses the same motion system, still uses the same extrusion system, the same nozzles, and so on as its, bigger, sort of higher temperature brothers up the line there, but it's designed to be just again, a utility machine you can put on the floor and use, sort of polyester materials, some nylons, things like that, and you can be successful all day long. But again, if you've got a higher spec material that you're really interested in, then I would go either to the standard, or if you're aerospace, then you really need the high temperature system. Okay, so the high temperature system works with peaks and PEX and PEI. That is to say, the Sabic, Ultem brand. We've qualified, many parts with our aerospace and Air Force customers using 180 HTs. Now, these are a single head system. Okay, so the one denotes a single head system. Okay, so this is a utility machine again, and we use breakaway support material strategies. If you have overhang or if you have geometries that need support, you just use breakaways. And we've done this with thousands of parts, and it works just fine. And so, that's a great, but again, single material, single head, single material on the 180s. When you switch to the 280s, you get access to different print modes. Okay, so the 280s have independent heads in X and Y. So you basically have the linear motor motion stage that I mentioned earlier. On the 180, you've got a single head that's moving around and it's printing apart and it's going real fast. Doesn't have to worry about clearance geometry calculations or anything else with the second head. It just flies. When you hit the 280i, you get access to these additional print modes. So if you want to run multiple materials, you can. If you want to run support materials, that is a water-soluble support, you absolutely can. If you want to run copy mode, by the way, and produce 2 parts at once, that's, tapping into some of that value proposition of the twin head machine. And then coming, at some point in the future will be an independent mode where you can produce 2 different, part geometries at the same time. The 280i is really a machine that we designed to be in some degrees future-proof, or at least future insulated, because the machine can get smarter as the software gets smarter. The machine can do things now that the slicing software isn't there yet for, right? So we actually have capabilities baked into the system that as the future, architectures of slicing softwares become more and more performant, then we will be able to allow our users to unlock more and more capabilities with that 280i and really, get that machine, to do, I think, really important things that are not available on either, a tied IDEX system where you share an axis, or on obviously a sort of a single head twin nozzle system. With that freedom of dual heads really will give you a lot of freedom for production applications, multiple part applications, multiple material applications for really a long time to come. And again, it's designed to be that kind of future-proof system. So, okay, let me talk about some case studies, right? So what have our users done? What have our customers done? So I'm just going to highlight about a half a dozen or so case studies here today, and just kind of give you that mind share about how these machines are used and where some of that success comes from. So start with Mercury Systems. Mercury Systems is a contract manufacturing business. This particular installation was in Arizona. They put a machine to work in their shop upstream of the actual wave flow ovens. So they had to print what's called a masking type geometry. So these are simple looking parts. You might ask yourself, why are you printing these parts? Well, the state of the art that this is replacing was basically tape. And so what would happen is, the componentry would be loaded on top of a circuit board, and then there would be tape or some other kind of manual application to protect sensitive components from going through a downstream process step where there were higher temperatures, elevated temperatures that would damage sensitive components. So what we allowed Mercury to do was to do away with an entire manual step. They already knew in their manufacturing software, they already knew the footprint that they needed to protect on top of circuit boards. So then they took that geometry of the footprint, turned it into an STL. They were able to then print the parts out of our TPU 95 ESD safe material, and also we have a nylon and a couple of different, even, a polyester ESD safe material. So they had a wide variety of options of kind of mid-range materials they could turn to that were temperature, capable enough to survive that downstream step. And so they saved a massive amount of money. The ROI on this system was probably less than about a month. And they were able to just really to move through their workflow. And this really, so the manual taping process introduced a huge bottleneck into their system, their manufacturing execution system, and we were able to remove that because of our materials and because of our again, open architecture machine that could just work with those geometries from their software. And it was very seamless for Mercury. So again, if you're thinking about like, a use case or where do the machines work well, again, this is a factory. This is not a design center. It's not prototyping. It's a factory where you've got a specific case. You need to get in there, print parts quickly, high performance materials, and keep the production lines moving, or let the production lines move more quickly. TTM technology, similar deal. Now, this was not, this was a fixture and jig application for downstream assembly of electronic devices. And so they used our PCTG Z material, and I'll talk about the materials here, in more detail in some of the coming pages, but they used one of our ESD safe materials to print fixtures and jigs for alignment of sensitive components. And you can see they actually printed in like the bosses for the part number of the jigs, and then they kind of came back with some whiteout or something like that, and made the part numbers really visual on their fixtures and jigs. But again, if you've got a need for a fixture or a jig for your a manufacturing or assembly operation, turn to HSE. It is the fastest and lowest cost of application for making fixtures and jigs. And if you got to make a bunch, let's say the design changed, and this little tower over here on the left-hand corner, that's got to move a little bit. Well, then you just print a new part. It's not a big deal. You don't have to take down a CNC mill or machine the part out of Delrin or do something else that just takes a lot of time. You've got the machine right there. It's flexible. It's a fixtureless machine, and it creates the fixtures and jigs right there on the factory floor for you to do that. It takes 5 minutes. In this case, it was really, really a big time and cost save for these guys. Axlebox, this is a fun company. So Axlebox is a sort of a design and manufacturing for service company. It's actually out of College Station, Texas. Again, Gigamags. And these guys, they've got, I think, 3, maybe 4 of our systems by now. So repeat customer. They use our systems to produce everything from drone bodies to, just a variety of other parts. I can't even get into, but this particular application was a drone body. They used 2 different materials from Essentium. They used our PACF, so it's a carbon fiber polyamide. That's a nylon, well, it's a polyamide 6/66. So kind of a mid-range, polyamide with a high degree of ductility, very, very ductile polyamide. No, it's not stiff at all, super ductile. That's important when you're making a drone because, drones sometimes don't land in the most graceful of fashions. You don't want the part to crack or break. So you want a material that's very, very ductile, but still has toughness. And that's where the carbon fiber came in for them. So selecting our polyamide carbon fiber was the perfect material for use for this drone body. And by the way, this particular project, I remember this was a project for a startup company out of California a couple of years ago when there were just really intensive forest fires in California. This company was basically designing a kind of a mid-sized drone. So I think it had 6, maybe 8 rotors. And it was designed to be able to lift and help forest fires. So you could lift, hoses up to the height of trees or the height of houses using the drone and, really giving firefighters another tool. So the materials also had to be able to survive a variety of high temperature applications. And so again, that's where our polyamide came in. They also, for their secondary material on this application, used our HTN CF25. That's an example of our multi-layered filament. And I'll get into what that means here in a couple pages, but for another great example of a material for a drone application was this high temperature nylon. HTN stands for high temperature nylon. So that is a polyamide polyphthalate blend. So PA/PPA blend on the resin side. So you got diblock copolymer chains. They come together. Permit me my material nerd moment, please. It helps me on the inside. And so, you bring these 2 material diblocks together, and then you supplement that with a high amount of carbon fiber, 25% carbon fiber. And if you're familiar with what some other competitors offer, it's 10 to 15% carbon fiber. So we could do 25% carbon fiber. And how do we do that? It's a pretty interesting secret. And I'll tell you the secret on the coming pages, but 25% carbon fiber, high temperature nylon resin. That's, again, it's a nylon combined with the polyphthalate, an amazing material. This is one of our most requested, most sought after materials. And it was used here again in this drone application. Very strong. Material is incredibly strong. The compressive strength of HTN CF25 matches the compressive strength of aluminum. It's incredibly, incredibly strong. All right. What do we do with Reebok? Man, Reebok, I love this project. So this project was took place a few years ago. And if you want to Google it, you can find it under the Liquid Factory. They basically, we're designing a process to go into production with a metal moldless line of footwear. So Reebok, this is Reebok North America out of the Boston facility. Hats off to these guys, highly creative. and really looking for opportunities to try to bring a portion of footwear manufacturing back to the United States. This whole idea, Liquid Factory, was the whole idea was, how can we use a high degree of automation and make shoes that we can afford to produce in high-cost countries? Again, addressing the supply chain issues that are so present in the world. I mean, look at the Suez Canal, look at, the Panama Canal, by the way. If it's not a good time to be a canal. But all the supply chain issues are there. And so, producing in a local fashion or in a regional fashion is always thought of as one of the key options that additive manufacturing unlocks, and we help them unlock it, actually. So this picture is a little fuzzy, but what it is a last. It's a footwear last of a shoe. This was printed from a custom resin, by the way, that we worked on and we produced in our factory, custom resin for Reebok. And so this had a polypropylene glass fiber, filler. The polypropylene was important because when you print with polypropylene, you get a nice non-stick surface, right? So then in a subsequent step, you go from the last to the next step, and then they 3D printed basically the shoe, a component of the shoe itself. And again, this is all online. I'm not, this is Liquid Factory stuff. It's on YouTube. Go look it up. It's pretty cool. But we partnered with them to make that happen, and this happened before the pandemic. Pretty exciting project to be part of. And again, we worked on the resin, we made the filament, we made the print profiles, we partnered with Reebok to help them out, and they bought multiple systems and developed the entire process to be able to go into production on a metal moldless line of footwear in high cost countries. Right? Very, very difficult to do. Gotta get some water. Hang on. All right. So Cam Kozlowski. So if the name Kozlowski is ringing any bells, and we've got any racing fans in the house, Brad Kozlowski is a highly accomplished NASCAR driver. He races. I think his number is number 2. I know he used to be Penske number 2. Now I think he's got a different team. But Brad is an amazing guy. Instead of taking his winnings and buying car dealerships, and I'm not saying anything wrong with that. I'm not throwing any shade. That's fine. But what he's doing is he's taking his money and he's putting it into advanced manufacturing. So he built CAM, which is Kozlowski Advanced Manufacturing. It's in North Carolina. It's an amazing machine shop that uses both additive and subtractive together. Okay, so he's got all different flavors of additive. He's got extrusion. He's got laser powder bed fusion metal machines, and then he also has subtractive. He's got Mazak machining centers and maybe some Haas. I don't remember all the machining centers he's got. But what he does is he prints high-spec preform parts, and then he'll take those high-spec preform parts, he'll go downstream to his own CNC, and he'll do the machining, whether it's creating threads or datum surfaces or sealing surfaces or whatever, and he'll take those parts and then, finish them on the CNC mill, and then, send them on down the road. But he uses our systems for fixtures and jigs and so on. This has been a huge time save for him throughout his operation, because his operation is kind of this mid-sized machine shop operation. I talked earlier about a lot of factory applications, large enterprise, large blue chip, large kind of, again, the Mercury TTM. There's many other examples of like high, very large enterprise. This is a mid-sized machine shop, high spec, high flexibility, high mix, a lot of different, small batch size, high mix. And so we put machines on the ground that help them be flexible, and again, worked in an additive, subtractive workflow together. Really exciting project. That was a lot of fun. And then finally, on the military side, we worked with our partners at the Rapid Sustainment Office, the Air Force Lifecycle Management Center, LCMC EZP, the Engineering Directorate, underneath AFMC, which is the Air Force Materiel Command. And so, yeah, so military, right? I mean, the military uses a bunch of old stuff, like most of the planes and most of the the backbone of the military here and with our allies. And you see it all over the world, is old vehicles, right? Olds, whether it crawls or drives or flies, most of the stuff is old. You've seen stories of certain bombers that the United States built back in the 1950s and are flying today and have a planned service life of 100 years. And when it's an airplane that flies around the world all the time, and it's going to last for 100 years. I mean, just think about that. It's mind blowing. So how do you sustain these systems for their entire life? The original manufacturers of these vehicles and these aircraft don't even exist anymore. They're gone, right? So the Rapid Sustainment Office was formed as a part of the Air Force, tasked with, and this was set up back in 2020 by Will Roper. He was the Secretary of the Air Force for Acquisition Technologies and Logistics. Brilliant guy, brilliant guy. He set up the RSO and he said, okay, I want you guys to be able to have the mandate to sustain America's fleet of aging aircraft and do so on a rapid basis, because we can't rely, we the Air Force cannot rely on always being able to source parts from a supply chain which may not even exist anymore. I mean, you think about the supply chain challenges that are tough today for like consumer device electronics, shoes, footwear, computers. Imagine you're flying a bunch of old stuff and the companies that built it don't exist, right? That's a true supply chain challenge. Imagine then that you have to sustain that device downrange, and things that are flying over your head, and they're those things are meant to hurt you. Like, this is a difficult task, right? A difficult task that the RSO has to do. And so we've been working with them for 4 years now on multiple parts. And so early on, they used a third party, University of Dayton Research Institute or somebody else, and they looked at high-speed extrusion. They're like, okay, what is this HSC really about, and how does it work compared to FDM? So this was a case study that looked at side-by-side production of an FDM solution along with our HSC 180. So people are like, well, 180, why would I want a single head system? Let me just go for the twin head system. The single head system is an amazing system producing complex parts, and you can do so all day long. And, again, highly skilled users have no trouble with that whatsoever. And so I really, I recommend the 180s for a variety of applications, but not the least of which, wide pipes. So they said, okay, we can produce this part in about an hour, whereas it takes, well over 560 minutes in other applications. So if we had to produce, over a 30-day period, how many pieces could we get? Nearly 300 on the Essentium system. And then they looked at a series of other applications. They said, well, what's the cost save available, right? Because we talk about how we are the lowest landed cost available for any true industrial system. And so, they found an 80% cost save for existing geometries on a tow bar that they were printing. They found 81% cost save on a bolt carriage inspection tool. They found 79% savings on ground support split cooling ducts. So that's using an Essentium system with our production speed advantage and our materials, right? So our materials are priced in a very competitive way. We're not here to make $1 bajillion on materials and only sell like 4 kilos a month. I don't care about that. I want to sell 4,000 kilos a month, and we're going to make the margins in a reasonable way so that we can promote adoption, because we want the world to print more stuff. That's so important to us. Prosthetics and orthotics, we have a series of materials. We have 4 different grades of materials that are found and tested by the University of San Francisco and others to be biocompatible safe. So safe for contact with human skin, right? So this means that some of our clients turn to Essentium because we can have materials that can go into prosthetics and orthotic applications. We've got many examples of that. I'm going a little long on time, so I'm going to try to speed it up a little bit here because I want to make sure there's time for Q&A. Like I said, okay, so yeah, so we multiple systems and polymeric systems for aerospace parts, as I've mentioned. So aging aircraft, C-130s have been around again for 50 years, be around for a lot longer. We also have FOD covers. So we've got an anti-static material. It's a TPU 58 Shore A anti-stat material that comes in red, and it's designed to be red because you got to remove it before flight. So one of our customer applications was going in and printing parts to cover satellite geometries before satellites would get launched. So they would, cover sensitive components that they wouldn't want to get dust on them or any sort of foreign objects. So they would print these covers. They're TPU, so they're flexible. They can kind of squish a bit. And so they'll go over these sensitive components, and then they're red. They stick out like a sore thumb, and you remove them before flight. So that's, a key application again as well. So there are many applications, true industrial use cases. I really encourage you guys, we're happy to be here and coach you and walk you through this. Again, with our new partners at Nexa 3D, it's going to go really, really well. We're excited about that. And so just reach out and we'll show you how at the end of the pages, but a lot of different applications across the industrial landscape. Again, jigs and fixtures, tooling, end-use parts, prototypings, castings. By the way, one of the recent areas we've spent a lot more time in is casting patterns and casting core boxes. So the large size of our systems, near 700 millimeters or so in X, these systems can produce a lot of the casting patterns and casting cores that are too large to fit on some of the other systems that are out there. So the build size can be a real advantage, especially in the areas of castings. And that's something that just last year, 2023, we saw a flurry of activity in the casting space. And so we're excited about that too. All right, let me talk about materials. So the HSC and Essentium, if you pick up these products and start using them, you get access to a broad basis of materials. We've got over 27 different grades of industrial materials available. You can go to our website, Essentium.com, click on the materials link. You can see how the materials are organized, and I'll show another page about that here in a minute. We make both monofilament and multi-layered filament. So we're the only company in the world that makes multi-layered filament. The reason why that matters is because you can get high spec materials at low prices, right? Our prices are not crazy. You'll see that if you want, you know, we can buy materials through our web shop. But making a multi-layered filament allows you to do a variety of important things. So I remember I told you earlier, I would tell you the secret behind our HTN CF25. Well, the secret is it's a multi-layered filament. So we put that high spec, highly packed 25% carbon fiber core, and we put a thin candy coating around the outside of neat polyamide, polyphthalate material, the same chemistry, raw, you know, just neat resin. And that creates kind of this sheathing, like a glue sheathing. You can almost think of it like a sausage. In fact, one of our guys, you know, used the illustration of a sausage with sausage casing, keeping all the good stuff on the inside. There's kind of a thin casing shell that keeps all the good stuff on the inside of our filament materials. Many of our high-spec materials, both the high-spec carbon fiber materials and the ESD safe materials. So we use multi-walled carbon nanotubes. We put these into a polymer master batch. We let them down to very, very low concentrations, less than 1 gram per kilogram, which is 0.1%, less than 0.1%. But we get clean room safe, consistent ESD properties because it's a nanomaterial concentration that has been nicely dispersed and yet encased, fully encased in a polymer master batch. So you don't have to worry about nanotubes flying around, getting in the air. This has all been tested. The Belgian government, in fact, did a series of exhaustive tests on these materials. The US government has done similar things. These are safe, easy to use, and they go out and they produce an amazing, consistent ESD performance with, again, providing a clean room safe environment because of the polymer master batch that encases this entire thing. But it's a core shell structure. I don't need to put nanotubes throughout the entire filament. I can just put nanotubes where I want them, which is right on the edges. And that's an architecture and material science win that we love bringing to our customers every day. Here's a snapshot of our filament portfolio. The stars are kind of indicating those that are the ones that are sold, you know, in the highest volumes and used the most. So general purpose, these are materials that are going to work great on the LT machines, the flexible materials, except for Duratem. Duratem is actually a material we just launched last year. It's an Ultem-like material that has a lot of ductility and toughness. So we basically modified the polymer backbone of polyether imide. I won't get into detail how we did that because it's super esoteric. I love it, but if you want to learn more, reach out. But we modified the chemistry of Ultem in order to make it more flexible. So now if you print an Ultem part and you like drop it on the floor or something, you don't have to worry about, did I crack my part? Because Ultem, incredibly brittle. It is so brittle. The material is so brittle. So by creating Duratem, we've created a durable Ultem, and that material was just launched last year, and we couldn't be more excited about it. But you need a high temperature printer in order to print it because it still has the Ultem polymer backbone, still passes the flame, smoke, and toxicity and V0 burn, you know, critical tests that Ultem has to pass. Duratem passes all those, which means it's useful for aerospace in-flight parts, which we love. All right, high temperature materials as well. This is where you start getting into needing the HT on the 180 side. By the way, the 280 only comes as HT, so you don't have to worry about, you know, the 280i, you can get, you know, all of Essentium's materials, right? And then fiber reinforced materials, then you've got your ESD safe materials, everything from the same PCTG chemistry. PCTG is like PETG, but it's got 10 times the impact toughness of PETG. So if you're used to using PETG, you should really be using PCTG because the impact toughness is 10x higher. Same cost, same polyester backbone, been slightly modified with some, you know, dangling moieties that make it much higher on its impact strength. And I can't get over how amazing that material is. Again, HTN. So you see, if you see a Z on it, you just know that that material is multi-layered because the Z basically means that it's got that thin candy coating of the nanomaterials that provide, you know, the ESD safe properties. So that's what the Z designation means. Okay, so how are these materials used? I'm not going to go into all the detail here on this particular page. Just know that when you work with us, when you sign up to work with us, we will coach you. We will coach you through tooling applications, jigs and fixtures, masking, automotive, energy, and aerospace. And there's all kinds of applications within these verticals. And how do the materials match up, by the way? I'm so glad you asked. The materials match up perfectly, and we've organized our materials to go in to all these different vertical spaces. And we'll coach you through this. Don't think you have to, like, you know, learn or absorb or understand or retain all of this right now. You can, you know, we will coach you through this, and you know, we'll provide, you know, more webinars, we'll provide more coaching, and of course, you can always find all the information you would want on our website. We also, by the way, offer dry boxes. Dry boxes are so important, guys. So whether you're printing from a liquid photoresin system, a powder bed fusion system, or a filament-based extrusion system, that raw material needs to be kept dry. And the way you keep the material dry and provide flexibility for material changeover is by using a dry cabinet, a very high spec dry cabinet. We call it a dry box. This is a material storage cabinet that'll store resins, powders, or filaments. It's, again, open architecture system. This is a really high spec material storage device. It has rapid recovery down to very, very low relative humidity. It's got this nice, indicating light system. So if you leave the door open for too long, it turns red and it starts beeping at you. It's like, hey, you're letting in all this moisture. Don't do that. So, people can close the door. And then when it's pumping down, and recovering and getting all the moisture out, it's yellow. And then when it's really happy, steady state, it turns green. So you can see that. And by the way, it's network connected. So you can actually see if you care about your high spec, workflow, and you're like, I need to know that this material was kept safe for, months and months, which by the way, you can easily do with these cabinets, then you can actually monitor that system online. You can see when was the door opened? Was the door left open? Is this material, at risk of being, exposed to too much moisture? And you can really use these systems for that. And these are available again for sale. So, whether you buy an Essentium HSE printer or whether you have other systems, you can buy these from Essentium, Nexa 3D, and use these in your ecosystem. So one of the last pages here, do want to touch on the pipeline. So we are still in the engineering, late stage engineering activities for our HSE 240. The 240 is around a 40 centimeter build tray. So, all the performance of HSE on a smaller footprint. This machine was designed to fit through like European width doors. So like 800 millimeter door, you don't have to have a loading dock or some sort of dual door device. It's designed to go down hallways. But again, it's got a 40 centimeter build tray, so it's a smaller machine, right? It does have a high spec servo motor, linear motion stage, all the same kind of guts of an HSE 180 or 280i are present in the HSE 240. It is a single head twin nozzle system. We couldn't package IDEX in a way that really made sense, in a small package. So we went with a single head, twin nozzle. The nozzles move up and down. Still in a full servo motor on the extrusion drive, high torque. This thing's got torque, for days. And so, again, this will come out. This will come out soon. It'll come out later this year, and we'll talk about, timing on this as we get closer to launch. But I definitely want to just, if you've seen these at trade shows, just know we Essentium have been working on this product, and then now we Essentium Nexa are working on the product, and we're going to, launch it, make sure it's available through the Nexa channels. And we'll talk more about that as the timing gets closer. World-class service and support. Yeah, definitely. We are here to support our customers. When you use an open architecture system, you need high touch support, and it's just the reality. So, we are here to support you, and we're going to do that, and we've done that for all of our customers. We've had great customer testimonials, really great ratings on our service and support to make sure that folks can be successful using an open architecture system. Because a lot of folks think, oh, I'm ready for all that freedom. I'm ready for going fast at high speeds. It's like jumping into a Formula One car. I'm so excited about going fast. Well, if all you need to do is go and get groceries, then you might crash that car. And we've seen that, and it's okay. It's okay. We're here to support you. And we're going to do that at a high touch, in a high touch way. So with that, guys, that's all the content that I had for today. This leaves us about 15 minutes for Q&A. And so happy to make sure we get to all those Q&A questions. If you're ready to take the next step and learn more, email us. Email us at sales@essentium.com. There's also, if you're a Nexa 3D user and you want to email, Nexa 3D, then Lewis, what email address that might they use to email on the Nexa side? I should have put that on there, and I'll do that when we distribute it. But
Surprisingly, very similar. Sales@nexa3d.com.
Look at that. Look how aligned we are. It's such a beautiful system. All right, guys, look, thank you all so much for your time. I love talking about all this, as I hope you can tell. And now we'll turn it over to questions at this point.
Let's go ahead and dive in. First question is it says, what kind of materials does every version of your printer print with? Is there an easy way for someone to see kind of what materials align with which printer?
Yeah, absolutely. So if you go on our website and go to Essentium.com, then you can click on, there's a materials drop down. There's also a 3D printers drop down. So you can select, like if you want to see the ST, like the 180 ST, for example, you can select that and then go in through our website, and it'll show you the compatible materials or the recommended materials for that system. So the website's the best place to go for that.
Thanks, Blake. And to clarify, we've got a little over 30 different filaments in the portfolio for HSE.
So some of our filament materials are useful in different verticals. So in some cases, we'll put a specific grade into, a vertical for footwear. We'll also put it into a vertical for consumer. We might put it into a vertical for fixtures and jigs. We have 27 different chemistries. So when you look at, what's the breadth of the chemistries, when we talk about a chemistry, we're not just talking about the resin, we're talking about resin plus filler plus architecture in some cases. So we've got 27 different grades that are made in our factory in Austin, Texas, 16 of which if you buy an HSE, you get pre-programmed slicing profiles for 16 of those materials. So you've got, an HSE with a slicing profile for 2/3 of our materials portfolio right out of the gate. And then you've got other materials you can go play with. If you want to go play with a material that, Essentium offers or someone else offers, by the way, these are open architecture systems. I don't need to mandate that everybody only use Essentium. If you want to use, another brand, go for it. We're gonna, you crash it, you still have to, go through warranty and get service and support, and that, that's gonna be a thing that we navigate together. But we've done that, and that's just like an actual manufacturing system. Again, a CNC mill, a lathe, a grinding machine, an EDM, whatever it is. If you crash the machine, then you learn and you go through and you dial it in and you dial in your process and you go from there and you're better the next day. And that's how we support our customers.
Okay, and then here's another really interesting question. So when you're printing in high speed versus like a low or standard mode,
Mhm.
what is the difference in terms of quality? And quality can actually mean a lot of different things. So I think
Yeah, I
when
can.
to mechanical performance and then maybe
Yeah.
aesthetics as well or dimensional accuracy. So I think that would maybe, if we can cover those three areas, would be a comprehensive answer to that question.
Yeah, absolutely. This is a fantastic question. I love this question. So, quality, we say that quality is in some cases in the eye of the beholder. What we mean by that is that, exactly to your point, Lewis, quality has different facets to it. So you might look at the surface quality of a part and the way that part appears in terms of the layers, being, stacked up one on top of one another in a certain way, the corners being completely a crisp 90-degree corner. There's not any stringing or any oozing or any artifacts from the print process still visible. Those may be the most important aspects of the part for you, because you've got to put this part into a customer-facing application, and you really want the customer to feel like, man, this is a high-quality part. And a lot of that quality perception that people have, myself included, it's those heuristics as we put a piece in our hand. If it looks beautiful, we inherently believe, man, this is a high-quality part. It may not be the strongest part. And in fact, when you print at high speeds, you get a stronger part. And the reason is because that layer that you are printing down on top of hasn't cooled down that much yet. So you actually get much better layer bonding when you print at higher speeds. Ergo, you get a part that is maybe 20%, in some cases 40% stronger in that Z direction with the same chemistry, same geometry when you print at higher speeds. So if you care about part strength, part performance, the performance of the part in creep or impact or low temperature failure modes, things like that, then you would want to print at higher speeds and you'd want to dial in that process. I don't mean to indicate there's a trade-off here between surface finish and part strength. There doesn't have to be. The low speed modes that we offer with Essentium's machines mean that right out of the gate, you're going to get a part. It's going to look like it was printed on an Ultimaker or a Fortis system or some other industrial system. You put it in your hands, you print at low speed, and because the speed and the temperature are constant on the Essentium system, just like those other systems. So, it produces a part. And if you got to print overnight and you don't necessarily, need to put that part into a demanding application, that's a great option for you. But if you have time to dial in the G code and dial in the process, then you can get higher speeds, higher mechanical property performance, and you can dial in the same surface finish. It might take you 3, 4, 5 prints to dial that in, because the way HSE works, and this is so important, we actually fluctuate temperature and we fluctuate speed at high speeds. Okay, so when you're approaching a corner, we let the nozzle cool down, and when you're approaching a corner, we slow down. So when you're in a straightaway, you're printing at 500 millimeters a second, your nozzle is turned up to 450 degrees. You would fry a polymer at 450 degrees if you weren't flowing material through the nozzle. So we then let the nozzle cool down and we slow from 500 millimeters a second to 50 millimeters a second when we're approaching a corner. That's what we do with high-speed printing. We fluctuate speed and temperature, aiming to provide consistent viscosity and consistent materials processing window to the polymer. That's the aim. But again, sometimes it might take you 3, 4, 5 tries to dial that in and really get it to where you pull the part off the machine. You're like, okay, the part looks like I want, but man, this is a strong part. It's a highly performing part. Now, by the way, now I've got the process dialed in. I can produce 50 of these things, and they're all going to look the same. So that's what when we talk about open architecture, we're trying to provide that capability for the user to choose. How do I need how do I need this part to be? When do I need to have the part? What are the requirements downstream? And then we give the user the ability to say, I want low speed's fine, or man, I need a bunch of these things, and I'm going to dial it in, and then unlock the kind of that full feature spec of HSE, and we support either way.
Yeah, I think it sounds great. It's kind of giving the user this, especially as you're just getting started with the system, some wonderful print profiles
Yeah.
that get in there really quickly, but then also the opportunity to take advantage of these more advanced settings to, dial the process, whether that be for speed or any other, characteristic
Yeah.
they might be seeking out, which I
Yeah.
think is awesome to kind of give them, sure, something to start with, and you're printing and making really great parts right out of the box. But then you have the opportunity to do so much more in terms of the flexibility of the system for more advanced processes.
It's a highly flexible system, Lewis. You said it well.
Yeah. So let's see. This is a wonderful question here. Um, what is the dimensional accuracy for parts printed at the 500 millimeters a second, particularly with high performance materials like Ultem?
Yeah, great question. Short answer is it depends, and I'm not trying to dodge the question, but we have two different nozzle sizes. We've got a 0.4 millimeter nozzle diameter, and we have a 0.8 millimeter nozzle diameter. So right there, you've got a wide range of different minimum feature sizes that those nozzles will support. We allow people to have a layer height, but they'll go from like 100 microns up to 500 microns. You can print a layer that's a half a millimeter tall, right? So if you're printing a layer that's a half a millimeter tall with a 0.8 millimeter nozzle, you're laying down a lot of material. So you're actually laying down material at like half a kilo an hour in some cases, right? So you're building parts really, really, really fast. So the dimensional accuracy of that part is not going to be the same as if you've sliced the part and you've prepared the part for a 100 micron layer height on a 0.4 millimeter nozzle. Your dimensional accuracy will be much better. Now, that doesn't mean that the mechanical system has changed in its dimensional accuracy. So the dimensional accuracy specs for the mechanical system are about 150 microns plus or minus across the entire motion system. 150 microns, so 0.15 millimeters. Now, again, you've got a mechanical system. We have optical encoders that run the entire length of our system. So the optical encoder combined with the servo-driven linear motor gives you a high degree of mechanical positional accuracy. Mechanical positional accuracy does not directly tie to the dimensional accuracy of the part, because again, as I just mentioned, you can change nozzle sizes, you can change layer heights, and so, but we have the system that again has the highest mechanical accuracy that we're aware of, because there's no belts, there's no pulleys, there's no rack and pinion systems. We don't even use ball screws in X and Y, just linear motors. It's a maglev train, baby. It's so fast, so accurate. But when you're looking at that feature size, you can dial that in and make it as accurate as you want to, given the nozzle diameter and those layer heights, and get incredible accuracy. The repeatability is a closely related question. Like if I print one part, is it highly repeatable? Yes, it's highly repeatable. You got to take care of the material. This is where the material custody chain matters a lot, because when you're printing, that material may absorb some moisture. Even though we've got dried canisters in our systems, there's no way to keep all the moisture out of a printer itself. There's like, some people would argue with me about that, and that's fine. I'm willing to have that debate, but there's really no way to keep the moisture out of the entire system while you're printing, especially if you're printing off of a 5 kilogram spool or an 8 kilogram spool or one of these things. So you've got to really take care of that material upstream. If you take care of the material and you're printing with, dialed in specs, you will get repeatable parts all day long. One of our customers, I didn't highlight, one of our customers, Ball Aerospace in just outside of Denver, Colorado, they've been printing on our parts on an average 13 hours a day, every single day for the last several years. And so they would not be doing that if they felt like there were repeatability concerns with the parts. Again, it's small aerospace. So our machines have high degrees of repeatability. But again, some of that workload is user dependent, right? So your user really matters. The person in the loop, the human in the loop, HIL, there's a human in the loop, and the human really matters. And so you get that user in there, this machine is going to sing for you.
Awesome. Thank you. Okay. And we have a couple of more, like some really great questions flowing through you guys. So thank you so much for this. Comparing with injection molding, and we get this question often.
Yeah.
What about the mechanical performance compared to a molded part,
Yeah.
particularly in the Z-axis?
Yeah.
And I think you touched on that a little bit earlier with the discussion around the benefits of printing at a high speed and how that can improve layer-to-layer adhesion. So I'll let you kind of expand there before, but I think you've done a great job of kind of initially diving in, and maybe we'll wrap up that one and give a complete answer.
Oh my gosh, yeah. So injection molding, we get asked this question all the time. So we actually started working on a technology back in the day called flash fuse, which was designed to provide underhead heating and electric fields and electrically active, capabilities in the chamber. So we have for many years been able to print, isotropic parts. What I mean by that is parts that perform with the same mechanical strength. So we use, ISO tests, dog bones. We compare it, I'm blanking on the test number right now. I want to say 590 or something like that. But there's 590, there's 720, there's several different tests that we look at for the dog bones of plastic parts. We've got an in-house injection molding machine, so we'll compare it right off of a molding machine part for the same chemistries. And so when I say isotropic, I mean like a material scientist would look at you and tell you this is isotropic, and we've achieved that. Now, this underhead flash fuse technology is not yet rolled out to these systems. What we could still achieve very high degrees of isotropy with certain materials. So some materials are just inherently great at this. I talked about PCTG earlier. PCTG in the ZX direction, the inherent isotropy is like 90 to 95% of the XY or YX direction. So it's an incredibly great material right off the print. And we've seen that with fracture lines, and fractures will go across the layer lines, right? So your layer lines are organized like this, and your fracture goes across the layer lines with PCTG so many times. We've got other materials like that. Our TPUs have a high degree of cohesion. It's called that interlayer bonding. It's not adhesion, it's cohesion. And so the TPUs are really good at providing that high degree of isotropy. Some of the other materials, not so much. If you've got a high degree of carbon fiber in your material, now our HTNCF25, since we put that thin candy coating of neat polymer on the outside, actually is fairly isotropic. But certainly that's something you would want to design for. So when you think about design for additive, I would still say it's highly necessary to consider the build orientation and that print direction. When you're organizing your part and designing your part and getting ready to print your part. But again, guys, I mean, injection molding is actually, I'm going in a rabbit hole here. It's actually not isotropic. Injection molding has a grain, it has a material flow, it has a directionality to it. This is actually well understood. So there are programs that do mold flow simulations, mold flow analysis. That's not just designed to move the sort of injection ports off the part. It's designed so that when the melt fronts come together inside the mold, that the engineers understand these are where your weak spots are in an injection molded part. All that said, I'm not casting shade at injection molding. It is the state of the art. It is a great technology. It's mature. It's been around for 60 years. Co-developed between Porsche and BASF back in the day. Actually, if you look at the history of injection molding machine and injection molding development, so that they could make gas tanks out of plastic back in the 1950s. Pretty cool stuff. But yeah, we think a lot about this. With certain chemistries, you can get really high isotropy. When you print fast, it gets even better. And then with other materials that you just have to design for additive, and that's where the design for additive comes in. So you understand your process.
What a wonderful response. I think that was you hit on it pretty well. Okay, so again, questions kind of keep popping in here, and I know we are right at time. So I'll go through just a few more for our audience here. We understand if you have to hop at the top of the hour. And if so, I want to let you know that we will follow up with you on answers to all of these questions so that you get that. And because we're getting so many questions coming in today, we can also perhaps share a little bit of an FAQ from some of these answers and responses, or you can come online and watch the recorded version that we're finishing now and complete the Q&A. But so starting with some really interesting questions. So what was the material used on the Air Force part that you showed?
The wide duct part, maybe,
So
or
yes, yeah.
yeah, that was the PACF, so polyamide carbon fiber. That was the closest material we could get on our system that would match a material offering on the classic FDM industrial systems. So um, polyamide carbon fiber. I think that they also looked at ABS, so there was an
Mhm.
ABS head-to-head comparison there as well.
Okay.
The materials that were used. Polyamide carbon fiber prints really fast, but it prints fast for everybody. The nice
Mhm.
thing about carbon fiber is it's thermally conductive, right? So you can get a really fast print with a carbon fiber um, material if you know your settings and so on. But that was a material we used for those studies. Yeah.
Awesome. And then I've got a series of questions really about the printer itself.
Yeah.
So first is, do you have a system that runs on plastic pellets? I'm sure you have a response for that one.
Yeah, we've not yet is the short answer. The way we designed the motion stage and the kinematic mass calculations that were used for the XY, we can support pellet heads. And so in fact, we've run pellet heads, multiple pellet heads on our systems. And so they run, obviously you slow it down a little bit, but with pellets you get high throughput. So yeah, we can, if you have a specific question about that, reach out to us at one of the email addresses and we're happy to share with you what we've done. We don't have like an off-the-shelf integration at the moment, but it's certainly something that we've looked at, and it may be something we commercially offer in the future.
Okay. And what sort of maintenance can be expected? You mentioned that a little bit earlier in the conversation. Other than
Yeah.
changing filament, what are some standard processes around maintaining the printer?
Yeah, the maintenance is actually really, really low touch. So we have with linear motors, you actually don't have to maintain you don't have to do prescribed maintenance at high intervals or anything like that. We typically recommend you go in and clean the motors and sort of clean the linear bearings. We use sealed bearings from THK. We had Bosch in the early days, and we upgraded to THK sealed linear bearings. Really, really good stuff. So the machine life is designed for 10 to 15 years, like it was a CNC mill. But the service life we recommend about on an annual basis. You go in, clean the motors, clean the rails, look at the grease levels, see if you need to, add any grease back into the bearings, things like that. I do recommend that you don't do an install in a dusty environment because of the magnets and so forth. If they get really dusty, then that's something that you would need to go in and kind of blow them off and sort of but you can do that because you can just lift the front of the machine. You get access to the entire, like I should say, lift the top of the machine. You get access to the entire XY motion stage. So you can go in and blow it off with an air hose or sort of clean off anything that might get very, very dusty. And when I mean dusty, I'm meaning dusty like you've put this machine right next to a powder bed fusion machine. I don't recommend that. We've had some customers do that. And when you have a high degree of contaminants like like nylon 12, plastic powder that's just in the air at high rates, it would be bad for any machine, but it was certainly bad for our machine. So, don't recommend that. But the normal dust environment that you would find in a factory has never caused us any issues at all. But certainly, again, high dust environments like next to a laser powder bed fusion, that's just going to be hell on any machine.
Okay. And then I'm going to make this our last question because I know we're over time and we'll follow up with the rest via email since we, have a lot to get through. But
Sure.
you mentioned a lot about the linear motor. So we had someone inquire specifically what kind of linear motor are we using? Is this iron core or ironless? And how does that affect the precision of the motor?
Well, we actually don't share the detail on our linear motor architecture. It's kind of one of our proprietary sort of trade secret type and things. We don't discuss that in our patents even, whether how we put the motors, like what the type of motors are that we use. But what I can tell you is that we use optical encoders. Okay, so there's two different types of encoders. An encoder is basically your device that goes along next to the motor axis, and it's just like a strip of material, and it's got tiny little markings, strip of material, and it tells the motor where it is in space. We use optical encoders, and so optical encoders are designed to work with all types of motion systems with varying degrees of ferromagneticity, and you don't have to worry about any kind of interference. And by the way, so optical encoders are magnetic encoders. Like magnetic encoders are just bad for all kinds of devices that you might have. your wiring and other things, will get interference from the magnetic fields and magnetic encoders. So the optical encoders that we use provide high precision and also minimize any kind of interference with other systems. So good questions. Yeah, good question.
For wrapping up, I think you've done a great job of explaining high-speed extrusion, how it really fits into the additive space, and I think it shows a lot of promise for everything from jigs and fixtures all the way up to a lot of production components. I think that was my big takeaway from this presentation
Oh
is
yeah.
seeing all the different ways that you can utilize this as an end user production part, right? Using
Mhm.
it on the production line or as the final part. But it's a really robust system that kind of gives you the control you need to achieve that. And coming from a service bureau environment, that's where I spent the large majority of my career before joining Nexa. I'm really impressed with that aspect of the system, is that it just gives you the opportunity to control and produce what you need to do. It doesn't you produced a system that doesn't get in the way of the user.
That's right.
So I think if for our audience that's left here, I would say that's my big takeaway from this. We will be sure to reach out regarding the remaining questions here. I want to thank everyone so much for your engagement here today. Blake, thank you so much for taking
Yeah.
time to
Thanks for
present
hosting those.
the products. And we will follow up with an email that you'll get probably in the next 24 hours that will have a link to the on-demand webinar. So you can feel free to watch that again, share with your colleagues and friends who you think might be able to get something out of this presentation as well. And we really appreciate your time today. Thank you so much.
Thanks, everyone.
Bye, y'all.
Bye.